Here we're going to have a look at the structure of benzene, and benzene has got the molecular formula C6H6, but it took some time for scientists to figure out what the structure of benzene was. The first thing they did was react this compound C6H6 with hydrogen, and benzene reacts with hydrogen in the following way to produce cyclohexane. From this reaction, you can deduce that benzene must be firstly a cyclic compound, because it produces a alkane with a formula CnH2n, therefore it must be cyclic. And because it required 3 moles of hydrogen to react to produce this cyclohexane, they also deduced that it must contain 3 carbon-carbon double bonds. That then gave rise, from this information, to the following structure being put forward. A cyclic molecule with the formula C6H6 with 3 double bonds, and this structure was developed by a scientist called Kekuke and is called Kekuke structure. Over time, evidence showed that this structure put forward by Kekuke was not quite correct, or was not correct at all, it shows. And the first bit of evidence was when we react this Kekuke structure with bromine water. And if Kekuke structure was correct, you would imagine that this carbon-carbon double bond would behave just like a normal alkene, and you would expect the bromine water to be decolorized. However, evidence showed that the bromine water was not decolorized. So basically, C6H6 didn't undergo electrophilic addition reactions. Second bit of evidence to disprove Kekuke structure was looking at the bond lengths. Now, if Kekuke structure was correct, the bond length of this carbon-carbon double bond would be the same as any other carbon-carbon double bond and be around 0.133 nanometers, and the length of the carbon-carbon single bond would be 0.1454 nanometers. When they actually looked at the structure of benzene and looked at the bond lengths, it was found that all the carbon-carbon bond lengths were equal. At 0.140 nanometers, they're actually somewhere in between the two, which is quite a damning bit of evidence to disprove Kekuke structure. The third bit of evidence we're going to look at is looking at thermodynamic data. Now, cyclohexene reacts with hydrogen to form cyclohexane, and in the process it releases 120 kilojoules per mole of energy. It's got a delta H of minus 120 kilojoules per mole. Now, if we look at Kekuke structure, we could reasonably assume, if Kekuke's structure was correct, because now I've got 3 carbon-carbon double bonds, we could reasonably assume that this would release 3 times the energy and would have a delta H of minus 360 kilojoules per mole. However, when we actually look at the enthalpy change for the hydrogenation of benzene, so we'll say this is the actual benzene rather than Kekuke's structure. When we look at the delta H there, is actually minus 208 kilojoules per mole. It releases less energy. And we can say, therefore, that benzene is 152 kilojoules per mole, which is your 360 minus 208 is 152 kilojoules per mole more stable than Kekuke's structure. The question is why? What, therefore, is the structure of benzene? Well, let's have a look at the diagrams on the top of this page. Now, we're going to have a look at one of these carbons. The carbon atoms are represented by black spheres, the hydrogen atoms by white spheres. So we're going to have a look at one of these carbons. We're going to have a look at this carbon here circled in blue. Now, carbon has 4 valence electrons, 4 electrons available for bonding. And this carbon that I've circled in blue, one of its electrons is being used to form a single bond with a carbon. Another of these 4 electrons is being used to form a single bond with another carbon. The third of them 4 electrons is being used to form a single bond with the hydrogen. The 4th electron is in a p orbital, a non-bonding p orbital. Now, what this means then is that each of these carbons has got a p orbital with an electron in it. And what happens is, because these p orbitals are very close together, they all overlap. And these electrons then are said to be delocalized above and below the plane of the ring. This ring here is a planar structure. And we see we've got delocalized electrons above and below the plane of the ring. And in this blue region here, somewhere in this blue region, there is 6 electrons. All 6 could be here, all 6 could be here, or we could have 3 here and 3 here. It doesn't really matter. There are 6 electrons somewhere delocalized in these what we call extended pi networks above and below the plane of the ring. And that confers extra stability. Now, if we look at Kekuke's structure, these 6 electrons would be fixed in these locations. And remember that the more that charge can spread around a molecule, the more that charge can spread, then the more stable the molecule is. So instead of the 6 electrons being fixed in these places, these 6 electrons now are delocalized throughout the whole ring. And we show that by a circle. So this circle then represents the fact that we've got 6 electrons delocalized throughout the whole of this ring. And in effect, that circle there represents the delocalized pi network. So we can finish this answer off now and say that benzene is 152 kilojoules per mole more stable than Kekuke structure, and we can say this is due to delocalization stability. That is that the electrons are not fixed in one place, they're spread throughout the whole of this plane of p orbitals that are mixed together above and below the plane of the ring. And that there is the structure of benzene.